Now that we've mastered all of the techniques of actually carrying out differentiation, we're going to transition to some of the more heavy-duty applications. Now, the quintessential application of calculus is optimization problems. So when you have some sort of mathematical model, how do you optimize a function of a variable? By optimization, I mean finding the maximum or minimum values. How do you minimize your fuel efficient or maximize your fuel efficiency, or maximize revenue or profit, something like this. So before we get into the optimization problems, we have to establish some terminology that's used to describe maximum and minimum values of functions. So to begin, we're going to just look at an example because the terminology that we introduce here is pretty intuitive. So without getting into the formal definitions just yet, let's just look at what the different types of maxima and minima might look like. Let me clear that a little bit. Let me just end it like that. So let's say I have a function and it's on a finite domain like this. And let me set this like that. Okay, so it's a little shaky, but that will do. So we have a function, it's only defined on this domain that's shown. So it's not defined anywhere other than the points that are shown. So there are things called local, minimum, maximum. The generic term for a minimum or a maximum is an extremum. So local, generically, extremum. And these are all the singular. To change this to plural, we change the um suffix to an a. So the plural of minimum is minima. The plural of maximum is maxima. And the plural of extremum is extrema. So the first step is to just identify the local extrema of a given function on its domain. So the local extrema are basically the minimum and maximum values locally. So local means if you just look close by. So for example, there's a dip right here, so that is going to be a local minimum, local min. But there's also a dip right here, actually. So that's also a local minimum. So we have a local minimum here and a separate local minimum right there. Right? So you can see that, let me just make this like that. If we just look close by, so just within this bubble, the point marked with the red dot is the single x value that generates the smallest possible y value. So it's a minimum value of the function occurs at that x value. And the same thing is true up here. So if I just look close by, right, out of all the points in that circle, the x value that generates the smallest possible y value is, generates the point marked in red right there. So that's a minimum point and a minimum point. There's also a minimum point right here. Right, so the domain ends, and it's not a smooth bottom of a valley type of minimum, but it's a minimum because the function starts here. So it starts at this value, and for all values of the function that are nearby, this is the smallest one in a small little region about that point. So that's also a local minimum. So those are the three local minima for this function. The global minima are found in a similar way. So this is the peak of a mountaintop. So that's actually a global, or not global, a local maximum. So that's a local maximum. And here's another local maximum. And then here's a third local maximum. So for each of these cases, if you just look close by that point, or this point, or this point, the point in red is the highest value, largest output value of all the neighboring points. So that's what's meant by local minimum and local maximum. Now the global extrema is a different story. Global extrema. So that it could be either minimum or maximum. So global just means that throughout the entire domain, this point generates the largest possible y value. So the global extremum, or the global maximum for the function that we have is the largest of all of the local maxima. So our global max is the one right there. Global max. So not only is this point this king over the neighborhood, the close by points, it's the king over the entire domain, or queen if you want. So it's the largest output value over the entire domain. And the global minimum would be the one, what color haven't I used? Let's do this one. So this one right here is, this point right here is the global minimum. So it's the smallest valley out of all the valleys. So local minimum, local minimum, local minimum. This local minimum has the smallest possible y value, so it's called the global minimum, right? So it kind of is the low point of the entire domain. So our task in this section and the following section on optimization is how do we actually go about finding these minima and maxima points? So how do we actually use the techniques of calculus where we want to have a precise location of a maximum point or a minimum point, and we can use calculus to obtain the location of these sorts of points. But first, let's introduce the definitions a little bit more carefully. So let's start with local extrema. Local extrema. So this first video is just used to introduce the nomenclature. So a local minimum of a function f, so we're defining local minimum, is a point x equal to a in the domain of f such that so f of a is less than or equal to f of x for all x values, two criteria in the domain of f that are sufficiently close by. And this sufficiently close by does have a more rigorous mathematical meaning. So there is a slightly more rigorous way to define this. Basically, the precise way is that there exists some open set that contains the point A. So there's some open interval surrounding the point A, such that for any x value in that open interval and in the domain of f, this inequality is satisfied. Right? So that open interval can be as small as you want, but there's some open set, it might be very, very small around x is equal to a, such that for all those x values in that open set, the output at x is equal to a is the smallest one out of all of the outputs in that open set. And then this is exactly the same if you just reverse the inequality for local maximum. For a local maximum, so we can just copy most of this. A local maximum of a function f is a point x equals to a, so that's the point A in the domain of f such that f of a is greater than or equal to f of x for all x values in the domain of f that are sufficiently close. Say to a. So to the point x is equal to a. And I suppose I should say the same thing up here. Close to the point x is equal to a. So close by or close to x is equal to a. So basically, if you're close enough to the point in question, the output at a will be greater than or equal to the output at any x value close to a, but still within the domain of f. Because remember, the outputs are not defined unless you're actually in the domain. So that's why that's an important caveat to add. All x values in the domain that are sufficiently close by. So let's take a look at the more rigorous way of defining this. So let's just focus on a local minimum at x is equal to a. So basically we said if f of a is smaller than f of x for all x sufficiently close by. So the way to actually do this would be to say the following. So local minimum at x. So if there exists a neighborhood. So what is a neighborhood? So basically it's just a fancy word for an open set or an open interval in our case. So an open interval that contains the point A. So an open interval that contains, okay, the T does not go at the end of that, contains the point x is equal to a. So a neighborhood is just kind of a fanciful word. It's used a lot in more advanced mathematics, topology, and analysis. But it's basically just an open set around a point. It's kind of a cute little term. So if there exists a neighborhood, and that just means an open interval, and let's give this name. So if there exists a neighborhood, which we'll call U, I kind of put this here. Let me move that. So if there exists a neighborhood U, and a neighborhood is an open interval that contains point, such that f of a is less than or equal to f of x whenever x is in the neighborhood U and x is in the domain of f. So in other words, x has to be in the open interval and in the domain of f, and that open interval has to contain the point A. So in other words, let's just look at a graph. Here's x is equal to a, and here's some function like this. So here's an open interval that contains a. So this open interval right there is our neighborhood about a. So that's an open interval that contains a. And the points on the graph that correspond to that open interval are just the points highlighted in red. So out of all the x values on this interval, the output exactly at x is equal to a is always less than or equal to the output at any other x on that open interval that contains the point A. So, the reason why we say there exists a neighborhood U is because we don't know how small it will be. It can be incredibly small, centered about the point A, but there's still some open neighborhood. So for example, if you have a function that zigs and zags a lot, right? So if you look very, very close and zoom in like 1,000 times, you might get something like this. And in this case, the neighborhood here might still be very, very, very small. But for some open set that contains the point A, f of A is always less than or equal to f of x for any of the x nearby. So there's just some open set that contains A such that this inequality holds for all the x that are both in the domain of f in order for f of x to even be defined and are in the neighborhood U. And then a similar sort of statement can apply to local maximum. So this is the technical way of saying close enough. So then finally, the definitions for global minima and maxima are much more straightforward because you don't have to worry about being close enough because their dominance extends globally. So a point x equals a is a global minimum of the function f if f of a is less than or equal to f of x for all x in the domain of f. So in other words, for any x value for which the function is defined, the output at the point A will always be less than or equal to any of the other outputs. It's the absolute or global minimum value of the function. And then similarly, a point, so let's say x is equal to A, is a global maximum of the function f if f of A is greater than or equal to f of x for all x in the domain of f. So for any other x value, it can never return a greater output than the output you achieve at the point x is equal to a. Now notice that I used the word a to describe a global minimum or a global maximum. And that was quite purposefully because it's not the global minimum. It could be, but not necessarily. A function can have more than one global minimum and more than one global maximum. Consider a simple example, f of x is equal to sine of x. Sine of x oscillates up and down. And so there are an infinite number of global minima and an infinite number of global maxima. So recall what f of x looks like this. And then let's draw sine of x. Not bad. And then continue. So here's pi, 2 pi, 3 pi, and then this is going to be pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2, 9 pi over 2, and so forth. So at pi over 2, we have the global maximum because sine of pi over 2 is greater than or equal to sine of x for all x values in the real numbers. So the sine of pi over 2 is equal to 1, and that's greater than or equal to all other outputs. But the same is true at 5 pi over 2. So 5 pi over 2 is also a global maximum. So see, they're tied. They're both given output value of 1. At 9 pi over 2, also a global maximum. And if it's a global maximum, by definition, it also has to be a local maximum. So every global maximum or minimum must also be a local maximum or minimum. So here we have a global minimum, global minimum, global minimum, and so forth. So there are an infinite number. So just because it's a global maximum doesn't mean it's necessarily the only one. There could be multiple ones that tie. So that's just a little caveat on the definitions.